In this video, we're going to be doing our first example problem using the first condition of equilibrium. To guide us through how we solve problems using the first condition of equilibrium, I have a handout that I prepared, and I'm going to be referring to this handout repeatedly as we go through this example problem. This handout has been provided to you in a couple different places within the Canvas module, first at the beginning of the Canvas module, and also in the link to this particular video. So it would be great if you are able to print this out and have your own hard copy next to you as you watch the video. And if not, another great option would be to watch this video on split screen with this video on one side of your screen and some version of this PDF on the other side of your screen. Okay, so anyway, let me introduce the example problem. So in this example problem, we have a ball of some kind, which is attached to the ceiling using two strings. One of these strings meets the ceiling at a 30-degree angle, and the other string meets the ceiling at a 50-degree angle. We know the tension in one of these strings. The tension in the string on the right is 43.9 newtons. We would like to find the tension in the string on the left, and we would also like to find the weight of the ball. So we're going to just start out following the handout. So the first step on the handout is to draw a sketch of the problem, and we already have a sketch of the problem here, although as we go through the process, we may develop the sketch. So let's go on to the second step. Step 2A says select an object from the sketch and draw a dotted line around the object. So the object we're going to be analyzing in this example is the ball. So I'm going to start by drawing a dashed line around the ball. Okay, and in your notes, you should do the same. Now we're going to start drawing our force diagram. And often when we draw force diagrams, the original diagram gets to be a little crowded. So what I'm going to do in this case, and in probably a bunch of other examples, is to draw a clean copy of the object off to the side so that the original diagram doesn't get to be too cluttered. Okay, so I'm just going to draw in a clean copy of the ball over here. Okay, so now going back to the handout. Step 2B, draw the gravitational force vector acting on the object. So the gravitational force vector will act down. So I will draw in a vector facing down. Okay, I'm going to label that as the gravitational force vector, G vector. Okay, so now that we have drawn in the gravitational force vector, we're going to try to identify any other forces acting on the object. This is where that dashed line comes in very useful, because basically in this class, the only force that can act invisibly is the gravitational force. Every other force we're going to encounter in this class can only act on an object through a physical contact. What that means is that if I go around this dashed line, every force acting on the ball other than gravity can only act on the ball by reaching in through the dashed line to touch the object, which means that I can identify all of those forces by just going around the dashed line and looking for where I see something reaching in through the dashed line to touch the object. So let's say I start here. I'm just going to start walking around the dashed line until I see something reaching in to touch the ball. Okay, here we go. So we have the string on the right reaching in to touch the ball, and that string will be exerting tension force 2 on the ball. So I'm going to come over to my figure and draw that in. Okay. Now I'm going to continue around the dashed line. And as I continue around the dashed line, over here, I see the string on the left reaching in through the dashed line to touch the ball. So over here, I'm going to draw in the tension force that the string on the left exerts on the ball. Okay, I'll call that tension force 1. Okay, so these are the three forces which act on the ball: the gravitational force pulling down, and then tension force 1 and 2. Now let's go to step 2D on the handout. It says label each vector, and I like to label my vectors twice, and this may seem a bit redundant when you first see it, but as the topic develops, you're going to understand why I double label my vectors. Anyway, what do I mean double label the vectors? I label every vector with one symbol indicating the name of the vector itself, and a second symbol indicating the magnitude of the vector. So here I have G with the arrow on top indicating the gravitational force vector, but then I'm going to go along the side of the vector and put G without the arrow on top indicating the magnitude of the vector. Similar with the other two, here I have tension 2 vector, but along the side of the vector, I'm going to put T2 indicating just the strength of that second tension force. And similarly, over here, I'm going to put in tension 1, just indicating the strength of that first tension force. Okay, and excuse me, I'm going to move one of these labels up to here. Okay, now I repeat, this may seem a bit redundant, right? Because here I just have G with an arrow on top, G without an arrow, T2 with an arrow on top, T2 without the arrow. It may seem like a lot of redundant work. However, as we go through the examples, you're going to begin to see why I do this and why it's so useful. Okay, so that was step 2 on the handout. Now, step 3, we're going to introduce a Cartesian coordinate system. Now, in future problems, we're going to try to line up our Cartesian coordinate systems so that the x and y axes line up with as many of the vectors as possible. In this problem, it's kind of a three-way tie. So if I would put my axes like this, let me use the protractor with the crosshairs. So if I would use my axes like this, I would align with gravity, but not the tension vectors. If I would align my axes like this, I would align with tension 2, but not the other two vectors, and so forth. So in future problems, we may try to set our axes so that we line up with as many vectors as possible. Here it's kind of a three-way tie. So we're just going to use standard orientation, which means we're going to have the x-axis pointing to the right and the y-axis pointing straight up, as you're accustomed to. Okay, so that's step 3A. Step 3B, if a vector is not aligned with either axis, determine the angle the vector makes with one of the two axes and indicate this angle on your sketch. Okay, so let's look, for example, at tension vector 1. We want to figure out the angle that tension vector 1 makes with either the minus x direction or the plus y direction. And to do that, let's come back to the sketch. Let's look at the string here. And I'm going to come into the figure and draw a horizontal like so. Now up here, you see a 30-degree angle. So if this is 30 degrees up here, what would this angle be? Well, perhaps you remember from your high school geometry classes that if two parallel lines are cut by a transversal, then alternate interior angles are congruent. So here, notice a parallel line and another parallel line. This line here, that's the transversal. And then this and this, those are the two alternate interior angles. So if this is 30, then this is 30 as well. Okay, so if this is a 30-degree angle, I'm going to copy that into the figure as well. Similar, if I look at this angle here between the string on the right and the horizontal, I have two parallel lines cut by a transversal. Alternate interior angles are congruent. So if this is 50, then this down here would be 50 degrees as well. And I can then copy that into the figure. Okay, so that was step 3B. Okay, so step 4, I'm going to spell this out a bit more than the sheet is asking for. Basically, what we want to do is work out the x and y components of each of the force vectors and enter them into a grid. So I'm going to just start by making the grid off to the side. Okay, so here's what the grid looks like. Actually, I'm going to do the grid down here. So here's what the grid looks like. Okay, so across the top of the grid, I'm going to list out the force vectors. So I have the gravitational force vector, and I have tension force 1, tension force 2. And for each of these vectors, I want to write down expressions for the x and y components of the vector. Okay, so my grid's going to look like this. All right, so now we're going to start filling out the grid. Into this box here, we're going to put the x component of the gravitational force. Now, you can see that the gravitational force is pointing entirely along the minus y direction, so it has no x component. So I'm going to put in 0. How about the y component of the gravitational force? Well, the entirety of the gravitational force is pointing along the minus y direction. So the y component is just going to be minus the magnitude, namely minus g. Okay, so now let's go to the tension vectors. So I'm going to sketch out tension 1 over on the side here. I'm going to give the tension 1 vector its own set of axes. We're not going to do this thing where each vector gets its own set of axes every time. This is just for the time being as we start to develop the material. So I'm going to take tension vector 1. Copy it over here. The magnitude of tension vector 1 is just whatever the tension in that string is. And now I can project tension vector 1 onto the axes. So here is the x component of tension vector 1. Here is the y component of tension vector 1. This is a 30-degree angle in here. So now remember how we find the components of vectors the quick way. For each component, we put down a plus or a minus, then the magnitude of the vector, then either a sine or cosine. So for tension 1 x component, you can see that that's along the minus x direction, thus minus sign. Then we have the magnitude is T1. Then T1x is adjacent to the 30-degree angle, thus cosine 30 degrees. Okay, then tension 1y component. So if this is T1y over here, then we could say that this is T1y as well. Okay, so tension 1y component is along the plus y direction, so plus. Then we have magnitude T1. And then T1y is opposite the 30-degree angle, thus sine 30 degrees. Okay, so now I'm going to take those and put those into our table. So tension 1x component is minus T1 cosine 30 degrees. Tension 1y component is plus T1 sine 30 degrees. Now let's do the same for tension vector 2. Okay, so as before, I'm going to give tension 2 its own set of axes. Right, you have a 50-degree angle in here. We're going to project the vector onto the axes to form the components. So I have tension to X component here. Tension to Y component over here. Okay, so now I'd like to write down the X component of tension 2. So it projects onto the plus X direction. The magnitude is tension 2. And then we have cosine of 50, because this is adjacent to the 50-degree angle. And then tension to Y component. So this lies on the plus Y axis, thus plus. The magnitude is tension 2. And then tension 2Y over here. This is the same over here. So you can see this segment is opposite the 50-degree angle. So I'm going to put in sine 50. Okay, now let's take those and copy those into the table. So we have tension 2 cosine 50 degrees, tension 2 sine 50 degrees. Okay, so let's go back to the sheet. So we have now completed step 4, which says to create that grid and fill it out. Now we're going to go to step 5, which is to plug our results from step 4 into the first condition of equilibrium. So the first condition of equilibrium says that if an object is not moving or moves in a straight line at constant speed, then the vector sum of all forces acting on the object is 0, which means in particular, the sum of the X components of the forces is 0, and the sum of the Y components of the forces is 0. Okay. So how are we going to sum all the X components of the forces to 0? Well, conveniently, we have listed out the X components of all the forces on the top row of this table. So all we have to do is add up all those elements in the top row of the table and sum them to 0. So that gives us 0 minus T1 cosine 30 plus T2 cosine 50 equals 0. So let's call this equation 1. Okay, now here we sum the Y components of the forces to 0. So reading along the bottom row, we have minus G plus T1 sine 30 plus T2 sine 50 equals 0. Let's call this equation 2. All right, coming back to the handout, step 6 would apply if we had multiple objects in the problem, and we're not there yet. So let's go to step 7, get cracking with the algebra. Okay, so let's do this strategically. We're trying to find tension 1 and the strength of the gravitational force acting on the ball. So let's look at what we have in the equations here. We're looking for tension 1, which appears in equation 1 and also in equation 2. And we're looking for the gravitational force. Now, you'll notice equation 1 has one unknown and equation 2 has two unknowns. So how about we start with equation 1 that just has the one unknown and use it to solve for T1. Okay, so I'm going to just take equation 1 and copy it down here without the 0. Okay, so now I can solve for tension 1. I'll start by just taking tension 2 cosine 50 and moving to the right. Okay, notice that I now have minus signs on both sides of the equation, so those can be canceled. Now I just divide both sides by cosine 30, so cosine 30 comes down here, and I have tension 1 equals tension 2 cosine 50 divided by cosine 30. Okay, now at this point, we're going to do a numerical substitution. And notice that I have not substituted any values so far other than the angles. I've kept everything symbolic. And you're going to be practicing doing that as well in this class. More on that later. But for now, I just want to point out that I have not made any substitutions except for the angles until I got to this last step where I'm finally going to solve for the answer. Okay, so tension 2 is given is 43.9 newtons. So I'm going to write tension 1 equals, you're substituting 43.9 newtons, then times cosine 50 over cosine 30. You can put this in your calculator now. I got 32.6 newtons. Okay, so that's the first thing we were looking for. The other thing we were looking for was the strength of the gravitational force. Anyways, now that we know tension 1, equation 2 here only has a single unknown, namely the gravitational force. So I'm going to just copy equation 2 over here. Actually, as I do this, let me put in a bit of algebra. I'm going to take these two tension terms and move them to the right. So I then get minus G equals, moving these guys to the right, minus T1 sine 30 minus T2 sine 50. Okay, notice that all of these terms have minus signs, so we can multiply through by minus 1 to turn those into plus signs. And now we can make our substitutions to finish the problem. Tension 1 we just found was 32.6 newtons. Multiply that by sine of 30 degrees, plus tension 2, 43.9 newtons. Multiply that by sine of 50. Put all of that into your calculator, and I got 49.9 newtons. Okay, so now we have solved our first problem using the first condition of equilibrium, and there will be many more to come.